Welcome to this short recorded video that will be going over parts of the solutions for the activities in the prologue lecture for the machine learning module, module 6 for the course Math 1376. So this first activity discusses linear polynomial regression. So the trick to adapt linear regression to nonlinear relationships between variables is to transform the feature data, also called the predictor variables. The basic idea is to create a linear model that looks like this: beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3, where the x1, x2, and x3 are actually just functions of the single dimensional input x. So in the case where you're working with polynomials, it just basically means this. You want y to be a function where like it's beta naught plus beta 1x plus beta 2x squared plus beta 3x cubed. So this is still a linear model where the linearity refers to the fact that the coefficients are never multiplied or divided or have any nonlinear relationship to each other. Or to the right, they're just there. They just have this linear, like you can change beta naught and it doesn't change anything else other than beta naught. And if you change beta 1, it just changes beta 1, right? They're not like getting multiplied together or divided, or there's not really complex relationships. So this is illustrated in this activity where what we work with is this data involving the sales data, this kind of fake sales data based on advertising. So we're looking at how to transform data by hand to fit a quadratic. Now, what you're supposed to do is add comments to each of the code cells below. You should really add it to every line to explain the individual lines of code in every code cell. Other than like what I'm doing, you can kind of just not add, you don't have to, you could edit the comments I have if you want, but I already provided comments for those. But you should comment here and here, like what these things are doing. And kind of like what's going on with these basic things. And sometimes if you have a lot to say, you might want to add like the comments like above, like at the top of the code cell, and write like a whole bunch more. That's kind of up to you how you want to format it, but you should make your code comments readable. And if you're going to have a lot to say, put it across multiple lines above a code cell. You short comments belong to the side of a code line, but longer comments should be above a code line. But anyways, in this initial part of the code, what I do is I create a copy of our original feature space, which is involving the TV, like X that has this TV data, TV advertising dollars spent. And the Y value, this is from elsewhere above in the notebook, involves the sales. So the idea in the model is if we have like Y equals beta naught plus beta 1x plus beta 2x squared, like if we have a quadratic model, beta naught represents how much we're selling if we don't advertise at all. We spend nothing on TV advertising. And then there could be a linear trend that we're capturing, and beta 1 is describing the linear trend part. Like how much do we drive sales linearly when we start spending on TV data? And then if there's a nonlinear relationship, how much is explained in the sales by that nonlinear relationship if it happens to exist. So all right, here we see x2. We insert in the 1 position, right? This is the 0 position because of Python indexing. This TV squared data, this is just like x squared now, right? In this example, TV spending is the x variable. So TV squared will be the x squared variable, and all we do is take that feature of x, TV, and we square it. And then we fit a linear regression to it. We have x2, which is this TV spending data. We have y, which is the sales. We look at the coefficient, and then we look at these the intercept and the coefficient. So the intercept is that beta naught. So we're going to sell like 6.1. I think these are in units of thousands, like 6,000 units if we do no advertising. And then based on the how much we spend in TV data, advertising, we have this explanation of how much we start to drive sales positively, and then there's this coefficient. Notice it's 3 orders of magnitude smaller than this one, which is really telling you it's a strongly linear trend, and there's only a slight nonlinear part to it, if you even think that there is. Like you can just kind of sometimes be fitting noise. That often happens with really complex models, is you think it's a complex model, but you're really just fitting like a high order polynomial to noise. But anyways, if you look at the score, which is based on the fit of the model, it is slightly better for the quadratic than it is for the linear. You can compare this to what was done above this activity, where we compute this r squared value, and it was 0.6118. And you can see this r squared value is 0.619. Like, that's hardly better. Like, it's really one of those things where it's, you can fit a 20th order polynomial if you want, and you're going to increase your R score possibly. It can actually go down, and it's because of the limits of finite data and some issues. Theoretically, it should always go up, but in practice, it can sometimes go down. But anyways, when you want to look at like how this actually responds, like if you want to generate a plot like what we've seen before, scrolling up, like this was just a cartoon example, but you wanted to generate like curves to see what the examples look like, or you basically say, I want to take this, which showed the linear trend of the data, and I want to show what it is with the quadratic on top of it, then that's where you have to say, okay, create like a bunch of fake X values, which is what's going on here. This is a data frame with fake kind of X values, and then predict the quadratic values for it, and then plot it. And then this is what you see. So, and I'm plotting the linear, right? I plot all the data. That's the scatter. And that's using the embedded plot attribute method within the within Panda's data frame that I can use, and just say scatter all the data where the feature space is the TV and the output space is the sales. And then I plot the linear predictions versus the quadratic. And you see like it's quadratic, but it's mostly linear over this range. It's not that much better, but it does, perhaps fit this little bit of nonlinearity that maybe seems persistent. Like when you first start spending TV dollars, maybe you get like a really rapid increase and then it levels off. So maybe a quadratic or a cubic may be a little bit better in terms of describing more local features that are present in the trend that a linear can't do. But like once you're beyond this initial TV spending, if you're spending more, it seems like a linear trend is generally better, even though there can be large variance around the trend. But at any rate, this wasn't here. I'm actually going to delete this. Like what it will look like for you is something like this. And I just started doing this before I made the video. And then I was like, I need to record this. So you're supposed to create cells below. You don't have any of these cells. Create cells below this. Like you're just going to have, here, I'll run that. You're going to have nothing. So you should create all these, like a bunch of cells. And then what you need to do is try, fitting a cubic. You're going to repeat this process above. You should change code comments, anything you have. And then you need to try something silly like a 6th or a 10th order polynomial approximation. And you need to answer in a markdown cell, what do you think is the best model and why? I'm asking the question. You need to answer it. Otherwise, it's just incomplete. So one of the things I want to show you is like, okay, let's say you make a copy of X with X3. So I'm going to run that. Now, let's say that I do the same thing I did before with X2, where I insert in the one position TV cubed, right? This is going to be wrong. I'm just going to show, like, this is what I had before, because I want to illustrate something that's incorrect. This now has a feature space that's TV and TV cubed. What it's missing is the TV squared data, because a general third order polynomial will have X, X squared, and X cubed. This really just has X and X cubed. So it's not a general cubic model that will be fitted if I try to do the regression on this, right? If I try to do this thing here with X3, I'm getting an incorrect cubic model with what I have below. So what you really need to do when you do the insert is the first thing you need to do if you're making a copy of X is like I'm going to rerun this so that X3 now looks here. I'll run this cell now. It's just the TV data, so that I recreated the copy. Create X squared, right? And then, in fact, I think what we'll do is, we'll do this. We could do this one at a time. Do it. Yeah, it's easier to just do it like this. Insert that TV squared data, and then also insert TV cubed. Now, what will happen if I have both of these in one? Let's go ahead and see. If I look at this, look, it put in that one position TV cubed after TV squared. So that's messed up. You don't want to do that. This needs to be 2. 0, 1, 2. That's the positioning. So let's just rerun this again. There we go. TV squared, and TV cubed. So now that's all created correctly. And now what you can do with this X3 is repeat this process above. A lot of this is copy and paste. So I don't think you need to see me do this, but make like LM3, but now fit X3. Now, there's a cheaper way to do this. You could do this a little more simply. You could have created a copy of X2 and then just run a line of code like this, if this was a copy of X2. And then when you go to, make an X6 or an X10 or something like that, just make sure that you're in, like, wherever you start from, if it already has TV cube data in it, for instance, like maybe you make a copy of X3, you got to put in the TV to the fourth, TV to the fifth, TV to the sixth, right? All of those things. Or, 7, 8, 9, 10, if you go all the way up there. And then what do you think is the best model and why? So you should repeat all of the steps up to creating a plot for all these things, including the cubic and either the 6th or the 10th. You could do both if you want. And you need to explain the best model and why. Now remember, the R squared will always get better, but I think you have a hard time arguing if you were talking to like a manager or a stakeholder that this quadratic model, just because the R squared value is marginally better than what you got with the linear, that actually means it's a better model. It's more complex, but you're kind of overfitting the data, in my opinion. I mean, maybe not. Maybe you're getting a little bit of this early trend, but I think if you were to play this out, like think about extrapolation. If you're spending more money, look at the concavity of this quadratic. This is going to decrease. Like eventually, you spend enough TV data, you're going to say, oh, you're going to have a reduction in cells. Does that make sense? So there's real issues with extrapolation in general with any model, especially models that are based on, like data over a range. Extrapolation errors are very bad, but the more complex your model is, probably the worse your extrapolation errors are, because your more complex model probably is overfitted to the data. And then it's just going to be less reliable predicting types of data it hasn't seen before, like TV spending that's in the 400s or 500s and whatever units this is. I think it was like thousands of dollars. And again, remember, you should add comments to all of these lines of code. And if you're copying and pasting after you've added comments above, you need to update any comments that were related to things above being squared data. So that's all I want to do there. Then I'm going to go to the last summary activity. You really need to read through this carefully and look for the highlighted questions problems that you need to answer. So up to now, all of the predictors have been numeric, and I ask you, what if one of our predictors was categorical? So let's create a new feature called size and randomly assign observations to be small or large, defining the size of the market. So you can imagine that you have like maybe really large cities where you spend advertising dollars versus either like rural areas or small like towns or municipalities, where you're going to probably have different types of effects based on the money that you spend on advertising. So this is what's done here. Now I set a seed. This is becoming something that you're seeing throughout this course. This is happening a few times just for reproducibility. And I create then a set of random numbers, uniform numbers, right? It's the rand, not rand in. It's not normally distributed numbers. It's uniform random numbers between 0 and 1 when it's rand. And I generate it according to the length of the data that we have. And then I create mask, and I'm basically saying, look, if I get something that's between 0.5 and 1, then that's going to be what's considered a large market. I'm just randomly generating them. And then otherwise, it's going to be a small market. So this is what I do, is I say I first set everything to small, and then I mask. I use the mask, excuse me, which is going to be these indices, right? This is a .loc, so this is taking all the indices based on this line of data. It's just a series of booleans where it's large and false. It's just those indices where this is true, and you can print this out, will be set to large. And so I print out so you can see like some are large, some are small, and then I ask you, you can look at this if you want to see what's going on. Let's just so you can see what like is going on with mask large. Mask large. Notice it's just an array of trues and falses. So basically everywhere there was a true, there was a large. So there's large, small, small, small. True, false, false, false. And then there's a large, well, there's the true. That's how it works. That's how this mask works. I just basically created a Boolean series of things that were roughly half of them were true, and then that's determined which of these markets I randomly assigned to be true, or randomly assigned to be large. What is the map method in the code cell doing below? So for scikit-learn, what we need to do is represent all data numerically. If the feature only has 2 categories, we can simply create a dummy variable that represents the categories as a binary value of 0 or 1. So what I'm doing is saying, look, I want to say I want to create data in a new column is large, right? And what I'm doing is I'm mapping wherever there's a small to a 0, and wherever there's a large to a 1. So larges became 1s, smalls became 0s. So now I have this new category where there's just 1s and 0s. So let's redo the multiple linear regression and include the isLarge predictor. So when I do this and I create this feature where I say, here's these feature columns, look at these sales, here's this linear regression across X and Y, where X now has all the features, all the advertising media that we use, TV, I think radio, print, something like that. So then we create our linear model. That's the LM, our linear model with this linear regression. We instantiate that blank one, then we fit the linear model with the data we have, and then we print the coefficients, and it's using zip, right? So there's all these little features we're pulling together, all these little things we've learned across all the earlier modules in the course, and I'm just printing what I and J are. Look for I and J and zip. Remember what zip does is it puts two lists or two items, arrays together, and then it's going, I want like the first component, which is the feature columns, and then the coefficient. So, the coefficient for TV is 0.045. The coefficient for radio is 0.188. Like, you can just interpret what all of these things mean. I read what it is in here, and I ask you to, what if you'd reverse 0, 1 in the coding? So now what I do is say, okay, let's talk about categorical predictors with more than 2 categories. Print out and comment on what the mask suburban and mask urban variables are and how they are being used. Now, I set the random seed again. I just did this because you might be rerunning things over and over again as you're playing with it. Normally, I would just set a random seed once in a notebook and never again. But because I'm anticipating that students would rerun code, I want things to be the same every time. So in this case, this is set. You'll see me set the random seed in a couple places here, but that's not, in my opinion, really good coding practice. You should set it once and just expect to run everything once. But if you're really rerunning code and playing with things a lot and doing things out of order, you might end up finding yourself needing to set a random seed just to control things a little bit more. But anyways, I say print out and comment on what the mask suburban and mask urban variables are and how they're being used. So I create these mask suburban and mask urban variables here, and notice everything is run, and I do this location with mask suburban and mask urban. So these things are based on logical conditions that determine a series of like trues and falses, and trues and false, like a true and false type of series. But I'm not printing what mask suburban and mask urban are. Like, what you need to do is like print, mask suburban, and you need, see, this is falses and trues, and you need to do the same thing with mask urban, and then you need to make some actual comment about how they're being used here. So I've pretty much, it's kind of like what we were just seeing, but you need to do it. I'm asking you to do it. It's in the instructions, so please do it. Print them out in code, and then add a markdown cell where you state what's going on, and then I have some other instructions, but I did all this other code. I'm just describing how we handle everything, because when there's more than one category, like there's rural, urban, and suburban, then I need 2 dummy variables in order to handle it. So it's like if it's 0, 0, it's rural. If it's 0, 1, it's urban. If it's 1, 0, it's suburban. That's basically what's going on. And then there's stuff about how to interpret what everything is going on here. So the only thing then that you really have to do, there's all the stuff you should still read and kind of go through and add comments to everything, is in code and markdown cells below, you should add more, meaning you should add more code and markdown cells probably as you're doing it. I ask you to repeat the above analysis, assuming there are 4 new categories to the data that you need to consider in the analysis. Call these 4 new categories ET, CT, MT, and PT for Eastern Time Zone, Central Time Zone, Mountain Time Zone, and Pacific Time Zone. These are the 4 time zones most people reside in within the United States. You get to choose how to randomly assign these categories to the data. You may want to look up the general population distribution in the US to estimate how to do this. So I'm not going to show this in a solution video. I'm just going to give you the idea of what to do. You need to look at what we were doing here with the area, which had rural, urban, and suburban, and how we had to use these masks here, 2 masks. How would you do this here? Well, this is describing, again, how you would do this with like k-1 dummy variables. What do you need? So you would need 3 dummy variables with 4 of these, and you need to create masks for 3 of them, right? Like do a default like Eastern Time Zone, and then you would have to create a mask. Like here I did a mask for suburban and urban, but not rural. So I defined everything for rural as a default and then used the masks in order to make suburban and urban. Well, you should maybe set everything to Eastern time zone and then create, based on population distributions, what masks should look like if you have, if you want it to be Central time zone, Mountain time zone, or Pacific time zone. And then you're just going to do something like this, except you're going to have an additional line of code and it's going to be with time zone. And then I just ask you to repeat. You're basically going to run something that's like this, and everything that follows it, you're going to do it below, and you're just repeating this analysis here. So that's, you are going to have to create more code and markdown cells to explain everything. So that's just what I'm looking for. I really want you to try to do that on your own. I'm willing to answer questions on the discussion board and help prod you along if you get a little stuck. But mostly students have done this well in previous semesters. But if you have any questions, by all means, please post. And then that's it. The last activity is the summary activity, so I'm going to stop the video there. Thank you for listening.